we go. Okay, so once again, we're going to be starting on chapter 8. We'll be discussing momentum, which is a concept that combines mass with velocity. And it's going to be represented with the letter P. And this is a vector quantity. Mass is not a vector quantity, but velocity is. And because of that, then momentum becomes a vector quantity. So we've already discussed a little bit about forces, and to know a little bit about forces is going to help us as far as understanding momentum. Sort of, we taught you that in order to teach you this. So we're going to take Newton's second law, which is force is equal to mass times acceleration, and we're going to change it around a little bit. So we're going to say that the rate of change of momentum of a particle is going to be equal to the vector sum of the forces acting on it. So what that means is we're going to look at the change in momentum over the change in time. And the reason we're going to look at things that way is because if we take the mass and the velocity and we judge how the velocity changes, then the mass times the derivative or the change in velocity over the change in time is going to be the same thing as acceleration. So that's how these two things link together. So the other key fact here that you're going to need to remember is that the total momentum of a system of particles is going to be the vector sum of the momenta of the individual particles. So in other words, when you go through and you add the momentum vectors of each individual particle, you can come up with the momentum of the system. So, and here you can see how the velocity vector is, when multiplied by the mass, produces a momentum vector, and then that can be broken down into its component vectors, px and then py. Okay, a lot of the first part of the section here is pretty much what we've already gone over. The only thing that you need to worry about is that momentum's units are going to be kilograms times meters per second. And this doesn't have any special name. Kilogram meters per second squared, you'd be looking at newtons, but this is just kilogram meters per second, and so that doesn't have any particular units. So let's see here. Again, this is a vector quantity. So let's take a look at an example here. If you've got two objects that have the same momentum but different masses, and which statement about them is going to be correct? The one with the smaller mass has more kinetic energy. Both objects have the same kinetic energy, or the one with a greater mass has more kinetic energy. So let's take a look at this. Momentum, again, is going to be defined as mass times velocity. So if the two objects have the same magnitude of momentum, in other words, P is going to be the same for each one of them, then the one with a smaller mass must have the greater speed, V. And kinetic energy, on the other hand, is going to depend on the speed squared. So the kinetic energy is 1/2 mv squared. You can express the kinetic energy in terms of momentum by saying 1/2 mv squared is the same as taking P over m, which turns out to be just velocity if you rearrange this equation. And so this squared times this leftover stuff over here becomes P squared over 2m. So if the objects have the same magnitude of momentum, then the one with a smaller mass is going to have more kinetic energy. And the reason for that is the denominator is going to be smaller. That means it's going to have a greater amount of energy. So the correct answer out of this is going to be A. So your components of momentum are going to be in the x direction, which is going to be, the mass is going to be the same for each one of these directions, but it's the velocity in that direction that's going to change. So you've got p sub x, p sub y, p sub z, and all of them depend on the velocities in that same component direction. And as addressed in the summary, the acceleration is going to be equal to the change in the velocity over the change in time. And if you multiply that by m, that's where the force comes into play. So you can see here, the mass is also multiplied by the right side of the equation, but this limit still stands. So if m is constant, then the right side of this expression is going to be the instantaneous rate of change of the momentum of the particle. So if m were constant, then we'd be looking at the change in the velocity, which is v2 minus v1. So going through and doing the multiplication here, you can see how that changes into the momentum of the second time interval, and this is the momentum of the first, and that's going to be the change in momentum. Rewriting all of that junk, this is what the end result comes out to be. So if you have a system of two or more particles, then you can define the total momentum of the system as a vector sum of the momenta. So if you've got two particles, summing together the momentum of that is going to give you the sum, or the total there for the system. You can also break that out into its components. Now, pardon me, momentum is sometimes called linear momentum. Right now, we're going to be dealing with linear momentum. A little later on, we're going to be dealing with angular momentum. When objects rotate, and we want to be able to express equations that will govern that type of motion, then we're going to have to start to come to terms with angular momentum. Concept's going to be pretty close to the same thing with a few changes, but it won't be, once you get the linear momentum, the other part will have you'll have a little easier time. So let's take a look here at this particular example. We're going to calculate the total momentum of two moving objects. So suppose a small compact car that weighs 1,000 kilograms is traveling north on Moorwood Avenue, speed of 15 meters per second. At the intersection of Moorwood and 5th, it collides with a truck with a mass of 2,000 kilograms and is traveling east on 5th Avenue at 10 meters per second. So treating each vehicle as a particle, find the total momentum just before the collision. So we set all of this up. This is traveling north, this is traveling east, and these are the situations. So we have momentum in the y direction, we have momentum in the x direction, and we will have, right before the collision, we will have a momentum vector that will look something like this. So to go through and to find it, you're going to find the momentum for A, which is this guy, in the x direction. Well, there's no motion, no velocity in the x direction, so that's 0. If we look in the y direction, we know what its mass is, and we know what its velocity is. So we multiply all of that out, and this is what we get. For the B, particle B in the x direction, this is what we have. It's 2,000 kilograms multiplied by its speed, and this is what we come up with. In the y direction, again, that particle is not moving. So we add all of the stuff together in the x direction. This is what we come up with. Do the same for the y. This is what we come up with. Using the Pythagorean theorem, we know that the magnitude of this is going to be this squared plus this squared, and then take the square root of that. If we want the tangent of the angle Then we can take y over x, do the division, and we come up with this particular angle. So that's pretty good. You've got a tutorial here that will kind of work through some of the other finer components of that, but that's generally what's going on there. Momentum is kind of a neat little concept in that regard. So let's take a look here at conservation of momentum. So we've got astronaut dude, and we've got a wrench. An internal force is a force exerted by one part of a system on another of the same system. This guy, along with the wrench, is considered to be a system. So an external force is a force exerted on part or all of a system by something outside the system. An isolated system is going to be a system that experiences either no external forces or external forces whose vector sum is going to be 0. So the total momentum of an isolated system is going to be constant. In other words, the momentum you start with is going to be the same as what you end with. And each component of momentum is conserved separately. So say, for instance, you've got an astronaut who's got a wrench, and then for whatever reason, he throws it. So you've got the momentum before here, and then you've got the momentum afterwards. So you've got when the astronaut throws the wrench, the total momentum of the system is conserved. Although the momentum of the astronaut afterwards and the momentum of the wrench, these are going to be different now. They're going to be different from the momentum of the system that you had before. Okay. So we've already gone over systems, internal forces, external forces, and what an isolated system means. The forces exerted by these two astronauts on each other form an action-reaction pair. So the force of B pushing on A is going to be equal and opposite to the force of A pushing on B. Again, the total momentum of an isolated system is going to remain constant. So let's take a look here at this particular example. We're going to consider conservation of momentum in an isolated system consisting of an astronaut and a wrench. An astronaut is going to be floating in space 100 meters from her ship when her safety cable becomes unlatched. She and the ship are motionless relative to each other. The astronaut's mass, including the spacesuit, is going to be 100 kilograms, and she has a 1 kilogram wrench and only a 20-minute air supply. So, thinking back to her physics class, she devises a plan to use conservation of momentum to get back to the ship safely by throwing the wrench away from her. In what direction should she throw the wrench? What is the magnitude of her recoil velocity if she throws the wrench at 10 meters per second? Will her recoil velocity be great enough to get her back to the spacecraft before she runs out of air? That's a sinister little problem here. So we're going to choose a system consisting of an astronaut plus the wrench. So we've got the ship here. It's 100 meters away. Here she is. She got the wrench. So we know the mass of the astronaut is going to be 100 kilograms. We know the mass of the wrench, it's 1 kilogram. So this is our system right here. Astronaut plus wrench. Now, afterwards, we know that the velocity of this thing, this wrench, is going to be 10 meters per second. We don't know what her velocity is going to end up being. So the basics here is that the astronaut needs to find a way back towards the ship. There needs to be a force that's going to send her back. So because the total momentum of her and the wrench is 0, she would throw the wrench directly away from the ship. all the vector quantities lie along the x-axis. In other words, we're going to make this a one-dimensional problem here. So we're going to be concerned only with the x components. So we're going to write an equation here expressing the equality of the initial and final values of the total x components of momentum. So we've got mass times velocity of the astronaut, all of this in the x direction, of course, and then the mass times the velocity of the wrench before, and then the same thing going on afterwards. So in this case, the initial velocity of each object is going to be 0 because they're not moving. So the left side of the, or not moving relative to the spaceship, that's, I should qualify that. So the left side of the equation is going to be 0. In other words, that ain't moving and that ain't moving, so all that just disappears. So solving for this, because we don't know what the velocity of the astronaut is after the wrench is thrown, and that's what we need to find. We're going to get the astronaut's x component of velocity after the wrench is thrown. So we basically take this and this, turn it around here, and we solve for this, and this is what we get. So mass of the wrench is 1 kilogram, mass of the astronaut is this, and then the speed at which it's thrown is this. So as it turns out, it's 1/10 of a meter per second. So the negative sign indicates that the astronaut is moving towards the ship opposite our chosen x direction. Chose direction to be positive towards the right. So to find the total time required for the astronaut to travel 100 meters at constant velocity, the distance is equal to rate times the time. This is what it is since we're moving in the x direction. Solving for t, we come up with 16 minutes and 40 seconds. So with a 20-minute air supply, wasn't a bad band back in the day, air supply, she makes it back to the ship safely with 3 minutes and 20 seconds to spare. So, and if you work the problem such that the astronaut only had 10 minutes of air supply left, you figure out that she has to throw it at 17 meters per second. So anyway, there are other problems there to work through, but that's an example there of one of them. So moving on to the next section, next two sections. So collisions can be classified according to energy relationships and final velocities. So in an elastic collision between two objects, kinetic energy is going to be conserved, and the initial and final relative velocities have the same magnitude. So in other words, you have a ball here, ball A, coming in, and you have ball B coming in. They have different velocities. They collide, they bounce back. And in this case, you could think of maybe a pool or billiards. They come back in, they bounce, and they go off of each other. In this particular case, energy is going to be conserved. And the initial and final relative velocities are going to have the same magnitude. You can have this vector and this vector are roughly the same, and this one are roughly the same. Now, in an inelastic two-object collision, the final kinetic energy is less than the initial kinetic energy. So you've got the same situation where they come in, they collide, boom. And with an inelastic collision, that means you don't have the same amount of kinetic energy that you started with. So you can see how this vector is a little bit smaller than this one, and this one is, or this vector is a little bit larger than this one, and this vector is a little bit larger than that one. And then finally, if the two objects have the same velocity, in other words, they stick together, the collision is going to be completely inelastic. So you've got your velocity vectors coming in like this, you've got your two objects that are coming together, wham, and then you've got a contiguous body here that is now traveling at a particular velocity. That is considered to be completely inelastic. So in other words, when the objects join together, they have the same velocity going on. Okay. Don't know if you've ever worked with these little air rails where you have compressed air coming out and pushing these little gliders along. But if you have, then you've kind of seen these things, and you can also see where you can put these gliders on, have springs on the end of it, such that you can have an elastic collision where they come together. They're not going to stick together, but that spring is going to have its energy compressed, or have its texture or composition compressed, and then it's going to release, and it's going to push these objects off. And so you had certain velocity B coming in, you got a velocity A going out, and then coming in. In a case where you have an elastic collision, the total kinetic energy is going to be conserved. With the inelastic collision, you're going to have kinetic energy be less at the end than what you started with. And again, finally, for completely inelastic collisions, you will see that these gliders will stick together and move away at a particular velocity. Now, if you have conservation of momentum, if you're concerned about that in a completely inelastic collision, this is the equation that you would use in order to address that. So it only is going to apply to objects that stick together after collision. So let's suppose that an object with mass ma, an initial velocity with this component, collides inelastically with an object of mass b that is initially at rest. If we use this particular equation, we're going to find out that the final velocity of the collective mass is going to come out and be equal to this. If we want to verify that the total kinetic energy after this completely inelastic collision is less than before the collision, we're going to do the following process. Using this expression for the velocity, the final velocity here for x in the x direction, we're going to find that the kinetic energies before and after the collision are going to be equal to these particular formulas. If we rearrange the terms, we find out that we can come up with a ratio of the final to the initial kinetic energy. And that ratio happens to be this. Quite a few problems. Let's pick one. So let's take a look at this one. So we've got a straightforward collision on an air track. So we're going to perform the collision experiment using these Velcro equipped guiders, or gliders, sorry. Glider A is going to have a mass of 0.5 kilogram, and glider B is going to have a mass of 0.3 kilograms. And both move with initial speeds of 2 meters per second. So find the final velocity of the jointed guiders and compare the initial and final kinetic energies. So we get things set up. We've got object A moving this way. We've got object B moving this way. The velocities are going to have the same magnitude, just different directions. Afterwards, after they've stuck together, the velocity is going to be in the x direction. We have no idea how much that's going to be. So that's what we're going to try to find out. So we know that the momentum of object A and the momentum of object B, if we add those together, it's going to be equal to the momentum of the combined whatever it is times the velocity of that whatever it is. If we take all of this information around, solve it algebraically, this is what we come up with. Because the velocity ends up being positive, then the gliders are moving together to the right after the collision. If we want to take a look at the energy before the collision, then we can see, we can plug in all the numbers here for this definition of kinetic energy, come up with this. Same thing for glider B, we can see that. So the initial kinetic energy of glider B is going to be positive, even though the x components of its initial velocity and momentum are both negative. So energy itself is going to be a scalar. So the total energy before the collision is 1.6 joules. Afterwards, we use this particular formula, we come up with 0.1 joules. So there's a substantial amount of energy that's lost in that collision in terms of kinetic energy. Now it just changes forms. So in an isolated, or in each one of these cases, the total energy of the system is conserved, just not the kinetic energy. Kinetic energy can be transmitted into other forms. However, in an isolated system, momentum is always conserved. There's no getting around that. Okay, so we've got all of our definitions here. If we're looking at elastic collisions, one in which the conservation of kinetic energy is applicable, then we can apply this particular form of, the kinetic energy beginning is equal to the kinetic energy at the end. And we can also apply the conservation of momentum in this particular case. So if we go through, and if the masses and the initial velocities are known, then these two equations can be solved simultaneously to find the velocities of objects A and B after the collision. So I say the general solution is a little complicated, so we'll concentrate on the particular case in which object B is at rest before collision. When object B is at rest, that means this term would disappear. It also means that this term in this equation would disappear. It turns into this. Let's back up here. All right. So two blocks, A and B, undergo a head-on elastic collision where B is initially at rest. After the collision, the two blocks move in the same direction. Which of the following relations must be true? The masses are equal, A is greater than B, A is less than B, or heck, I don't know. So the solution is this. So we're going to assume that block A was initially moving in the positive x direction. After the collision, block B must also move in the positive x direction. Therefore, both blocks have a positive final velocity. And a casual interpretation of the equation 8.11 reveals that the mass of A must be greater than B in order for the final velocity to be positive. So the correct answer here happens to be B. So if we look at particular cases here, we're going to say that object A is a ping pong ball, and object B here is a bowling ball. We're going to expect A to bounce back after the collision with a velocity nearly equal to its original value, but in the opposite direction. And we're also going to expect B's final velocity to be much smaller in magnitude. And that's just what you get when you go through the equations. Even though mass A is much smaller than mass B, the fraction in the expression for this is approximately equal to -1. So velocity in A is approximately equal to what it was initially, just pointed in the other direction. So what you're looking at here is A coming in, hitting B, and bouncing off at almost the same velocity, just in the opposite direction. It will cause a little bit of motion here, but not a heck of a lot. Okay, impulse. This is a concept that a lot of people may not necessarily know a lot about. And it's going to be represented with the letter J. So the impulse, J, of a constant force acting over a time interval is the vector quantity J is equal to F times the time separation, or F times delta T. So the change in momentum is another way of describing the impulse. So the change of momentum of a particle during any time equals the impulse of the total force acting on the particle. So you've got the force being applied over a set amount of time. When you take that time difference there and multiply it by the force, you're seeing the change in momentum. That is defined as J. So again, you see our definition here. And again, since we're looking at a change in momentum, the units are pretty much going to be the same as the units of momentum. That makes perfect sense. This is another more mathematically acceptable or legal way of putting that together. And again, we have defined force before as a change in the momentum over the change in time. So we combine this with equation 8.14, we're going to get the following relationship, which is called the impulse momentum theorem. So when a constant force acts on an object during a time interval, the change in the object's momentum is equal to the impulse of the force acting on that object. Impulse is going to be measured in components. So you can see the change in momentum in the components for both x and y. So we can also define an average force such that when F isn't constant, the impulse J is going to be effectively given by the average force over that change in the amount of time. So if we're going to approximate the impulse for a force that varies with time, we can take total interval from Ti to Tf and divide it into subintervals, which this is looking awfully calculus looking. Once we divide it into subintervals and we calculate the impulse as follows. So the impulse ends up, when you plot force versus time, this area under here is going to be considered your impulse. And this is what happens at specific points along the time interval. So you see the change in the force there. If you wanted to, we're basically going to change this shape into this shape. And we're going to do that by saying, well, yeah, okay, so the force changes from this point up to this point up to this point, and boy, that's, a lot of changing or whatnot, and I don't want to have to mess with that. So just give me the Reader's Digest version of what's going on here. And what that means is we're going to take whatever this force value happens to be, and we're going to average it out. And so we're going to say, okay, so the force, this thing behaves overall as the same average force acting at the same level from this time to this time. And that's how we're going to define it. So let's say we got a baseball player that's catching a fastball, and it lets his hand move backwards in the direction of the ball's motion during the catch. This maneuver reduces the force of the impact on the hand principally because, is it the speed of impact is lessened, or the time of impact is increased, or the impulse is reduced? Well, whether or not the hand moves, the change in momentum and therefore the impulse are roughly the same because the speed of the ball is much greater than any motion of the hand. However, for that same impulse, the relationship here shows that if we increase the time interval, we decrease the average force. In other words, let's say this number is 100. And let's say this is 10. Bad choice. Let's say this is 2. No, let's say this is 1. So we got 100 here, we have 1 here, and so the force there is 100. Catching a ball like that might hurt a little bit. But if we change that to say 2, we still need to produce 100 here because we're still trying to change, or we know what the impulse is. That's not going to change. But how quickly we execute this might change the average force needed. And if you double this up to 2, you'll cut this in half to 50. And so that reduces the force. So the correct answer in this is going to be B. So I got several other problems there to work through. So sections 8.6 and 8.7, center of mass. The coordinates x sub cm and y sub cn, that cm there is not centimeters, that's going to stand for center of mass. So the coordinates for x and y of the center of mass of a system of particles is going to be defined as this. You may have seen something like this before. This is actually a weighted average. In other words, it takes the mass at a particular point and adds that to the result of mass at a different point times this, plus mass at an even different point times its position, so on and so forth, and divides it by the sum of the total mass. You do all of that. This tells you where the position of the center of mass in the x direction is going to be. You do the same thing here for y. Why is that important, and how is my life improved by this? Well, the total momentum of the system is going to be equal to the total mass multiplied by the velocity of the center of mass. So the total amount of mass you've got multiplied by the velocity of the center of mass, whatever vector direction that happens to be, is going to be the sum of all of this, and it's going to be equal to the momentum of the system. The point is that you can take the entire object, no matter how big of a monstrosity it might be, and you can model its motion by just looking at the center of mass. And if you do that, it might make your calculations a little bit easier. The center of mass of a system moves as though all of the mass were concentrated at the center. So the sum of the external forces is equal to mass times the acceleration at the center of mass. So here's an example. You got a shell that's moving like this, and then boom, it explodes. Center of mass continues to follow the shell's original trajectory. In other words, this object, while it might have split apart, the shell is falling this way, and the whatever this warhead happens to be is traveling along this path now. It's going to behave as though the center of mass, as if the motion of this thing never separated and is following along the center of mass. So we've gone through all of those calculations here. Now, what is a visual of the center of mass? What does it mean? Well, for a cube, it's going to be pretty much right in the middle of all three cardinal directions here. For a sphere, again, you might imagine that being right in the center. Same thing for a cylinder. If a homogeneous object has a geometric center, that is where the center of mass is going to be located. If an object has an axis of symmetry, the center of mass is going to lie along it. In other words, you can put an axis through here, and it doesn't, what you see on one side of the axis is going to be the same as what you see on the other. Same thing is true of a donut. The interesting thing about the donut here as compared to the disk is that the center of mass is lying in a spot where there really is no mass. So that can be kind of interesting. Again, there's more conversation here regarding the velocity, the center of mass and whatnot. And more equations here even still. Let's see what we got here. Let's take a look at the quarreling pets. It's an interesting problem. So we're going to take those equations and we're going to apply it to a simple one-dimensional system. So we have a cat and a dog. I would assume that the way those things are drawn. So suppose a 2-kilogram cat, 2 kilograms for a cat. 1 kilogram is 2.2 pounds, so that's a pretty light cat, actually. And a 3-pound dog, that's a pretty small dog, too. I've got one. It's a Pomeranian, kind of cute. So let's say they're moving towards each other along the x-axis, and they're, of course, going to get into a scrap. So at a particular instant, the cat is 1 meter to the right of the origin and is moving in the x direction with this speed. And the dog is 2 meters to the right of the origin, moving in the minus x direction with a speed of 1 meter per second. I don't know. It seems kind of awfully slow for the dog, but there we are. So find the position and velocity of the center of mass of the 2-pet system and also find the total momentum. So we chart all of this out. So we got our animals here. They're about to go at it. So we want to find the center of mass of the 2-pet system. So we go through, we use our equation, plug in the numbers, and we find out the x component of the center of mass. We know where that is. If we're going to find the velocity of the center of mass, we're going to use equation 8.20, which is above. Plugging in the numbers, this is what we come up with. The total x component of momentum is going to be the sum of the x components of momentum of the 2 animals. Comes out to be this. Alternatively, the total momentum is the total mass times the velocity of the center of mass, and it should come out to be this. So in other words, if we sum it together like this, or if we look at the center of mass, we come up with the same answer. So that's pretty cool. Okay. So here we're defining the center of mass of a system. So say we've got this going on, and we want to figure out where the center of mass is. How would we go about doing that? Well, again, we're going to look at all different components, and we're going to sum together the mass times the acceleration of each one of these. As we do that, we come up with the total mass times the acceleration of the center of mass. Sum of all forces is going to be equal to the external forces plus the internal. Because of Newton's third law, the internal forces all cancel in pairs because they're just the same force acting, same magnitude of force acting in equal and opposite directions. So only the sum of the external forces is left, and so we come up with this. The acceleration of the center of mass is basically going to be the sum of the external forces is going to be equal to mass times the acceleration of that center of mass. So this is always a cool picture. Suppose the center of mass of an adjustable wrench lies partway down the handle. In other words, you see this white dot? That white dot is going to represent the center of mass. So this figure shows what happens when we send the wrench spinning across a smooth tabletop. The overall motion appears, fairly complicated, but the center of mass follows a straight line, as though the mass were concentrated at that point. And we've already gone through the shell exercise there. So anyway, thought that was center of mass is always an interesting concept, I think. Rocket propulsion. This is going to be the last section here that we'll go over. The mass of the rocket changes as the fuel is burned. Analysis of the momentum relationships must include the momentum carried away by the fuel, as well as the momentum of the rocket itself. So let's say we've got a rocket here, and at time t, the rocket has a mass m and x component of velocity v. So this is the positive x direction. V is moving in this direction. You got a mass here. The fuel burned is going to represent a change in mass, and that's going to be negative. That fuel is also going to be thrown out of the rocket at a particular velocity. It's going to be velocity times or minus the velocity. Let's see, what are they calling this? It is, I don't exactly know what it is. Let's see. I guess it's the I'm missing it here. Where is it? Okay, right. Okay. Okay, it's the exhaust speed of this material relative to the rocket. Okay, so this is the exhaust speed. So you got the burn fuel that's moving at v prime, which is equal to the velocity of the rocket minus the velocity that's of the expelled fuel. And then the rocket here is going to have some sort of change in velocity, and we're not exactly sure how that's going to reflect. And we know it's going to have a change in mass because the mass here should be the same as the total mass here. We're looking at it as a system. So whatever change in mass you've got here should be the same, just equal and opposite of what you've got going on here. So there you go. That's what we've got there. So at the end of the time interval delta t, the mass of the rocket, including the unburned fuel, has decreased to this. And the rocket's velocity has increased to this. Again, this is supposed to be negative. This is one of these problems where you've got to watch your signs as you go through. So the rocket's momentum is going to be mass times the velocity at that particular time. And thus the total x component of the momentum plus the ejected fuel at this particular time is going to be this, mass times velocity plus the mass times the velocity. This is an isolated system, therefore momentum is conserved. So we know what the momentum was starting out. This is what the momentum is going to be afterwards. Simplifying all that crap, we come up with this particular number of terms. We're going to ignore this term. Why? Because we're in a physics class, and in physics class, if the product is so small that it's not going to influence anything else going on, we get to throw it out. You try that in a math class, and you will not pass. But here, we're not going to worry with it, so boom, it's gone. This leaves us with this. We know what this is, the change in the velocity, the change in time. That is going to end up being acceleration. So we take mass times acceleration, boom, that becomes the force. And therefore, we've got ourselves a definition for the thrust of the rocket. So the thrust is going to be proportional both to the relative speed of the ejected fuel and to the positive mass of fuel ejected per unit time, which is minus delta m divided by delta t. And again, this is a sign issue here, as you have to remember as you go through. So that, and you've got a few problems there to work through. Not too much. Won't spend a heck of a lot of time on that, but I do want you to at least be exposed to that. So those are the basics of chapter 8. Do you have any, I know that's a lot of material to go through, and it went through it fairly quickly, but do you have any questions at this time about that?
No, I don't have any questions.
Okay. And this may not be that difficult of a material for you on this one. It seems fairly straightforward, I think, in most cases, but as you start, we say that, but trying to get through and starting to work the problems, and it can become a bit more of a hassle. So, but anyway, that's what I have for this evening. Is there anything else that we need to talk about?
No, I think I'm good.
Okay. All right then. Okay. Well, I'll go ahead and stop the recording here, and hope you have a good evening. And I will see you again next week.
Have a good night.
All right. You too.